Okay. Did you make any ha-has? Yeah. Okay. Yay, you did. All right. We're going to follow the same pattern we followed the last couple notes. We're going to write the formulas down. We're going to take a look at where they came from. We're going to do a couple examples. Yeah? Easy peasy. Don't judge me. I need my caffeine. All right, so let's start with the formulas. Just like the last couple, we have one for sine, one for cos, one for tan. And now we're looking at half angles, theta over 2. Theta over 2. Formula for theta over 2 is plus or minus the square root of 1 minus cosine theta over 2. And my hope is the inside of that fraction looks vaguely familiar. And the next two should illuminate that pattern a little bit more clearly. For cosine of theta over 2, cosine of a half angle, we get plus or minus the square root of 1 plus cosine theta over 2. Ooh. We know that tangent is sine over cos. So I can predict that my formula for tangent is going to be plus or minus square root. And then looking at sine and cosine, they have those same denominators. Those 2's are going to cancel. And I'm going to get 1 minus cos theta over 1 plus cos theta. Looking at those arguments inside the square root, where have we seen those before? They should look familiar. When did we see them? Do we see anything that looks familiar in our notes? Similar to the insides? I do. Yeah, those power reduction formulas. Sine squared is 1 minus cos 2 theta over 2. Cos squared is 1 plus cos 2 theta over 2. These are coming from the power reduction formulas. And I'm not going to go through that derivation. If you're like super interested, the book shows you very clearly those 3, and it's only like 2 lines. It's really fast. What I want to show you is 2 extra formulas for tangent and where those guys come from. So tangent gets 2 extra formulas that don't involve a square root, which makes them nice options sometimes. The first is sine theta over 1 plus cos theta. Or we could also have 1 minus cos theta over sine theta. Those 3 statements for tan of theta over 2 are equivalent. They should give you the same answer. Some of them will work better depending on what your sine and cosine fractions look like. Yeah. I want to take a look at where that first one came from really quickly, how we get from the square root to the non-square root, because I think that it's a useful tool to have in our toolbox. Yeah? So, we're going to start here. Tan theta over 2 equals square root of 1 minus cos theta over 1 plus cos theta. And my goal is to make it look like sine over 1 plus cosine. Ugh. Yuck. So, looking at that, I know this is where I am. I know this is where I want to be. And in order for that to happen, I need to get that denominator, 1 plus cos, out from under the square root. Which means at some point, somewhere in this process, I need a 1 plus cos squared. 1 plus cos times itself. Because that's the only way to get something out from under a root is square root squared. They undo each other, they cancel. So my instinct is to force that to happen by underneath this square root multiplying the top and bottom by 1 plus cos theta. Why am I allowed to do that? What's that red fraction equal to? Brittany, what's that one fraction equal to? It's 1, yeah. It's just 1. Yeah, anything divided by itself is 1. And multiplying by 1 doesn't change anything. I'm allowed to do that. That's not cheating. And I'm doing that because I know that the answer, the top may be ugly, but the bottom is going to be 1 plus cos theta squared. And I know that square root and that square will undo each other. That's going to give me the bottom that I want. Yay. Bottom's happy. Now I just got to worry about the top. On top I have 1 minus cos theta times 1 plus cos theta. How do I multiply binomials? Starts with an F. Foil. We got to foil that bad boy. First outer, inner last. So first is 1 times 1, which is 1. Yeah. Outer is 1 times a positive cos. So plus cos. Inner is a negative cos times a 1, which is negative cos. Last is a negative cos times a positive cos. Negative times positive is negative. Cos times itself is cos squared. I see 1 or 2 people nodding, and I don't see anyone disagreeing. I'm going to assume I did that correctly. Right? Foil. First, outer, inner, last. Just multiplying binomials. Do we see anything in the numerator that's going to simplify? Yeah. Positive cos, negative cos. Those middle terms cancel. If you are good at recognizing patterns, you may have recognized that those binomials are a difference of squares. And I would expect that I get a squared minus b squared as my answer, which I did. So if you are good at recognizing patterns, you can skip the foil. So let's rewrite so it looks a little less scary. The bottom I can take out of the square root. The bottom, the square root of the square is just this. Bottom's already happy. The top, underneath the square root, I have a 1 minus cos squared theta. What do I want on top of my fraction? I want a sine. Yay. It would be nice if you guys talked to me. Yes, I want a sine function. The question is, how can I turn a 1 minus cos squared into a sine? We have an identity for that. Does anybody remember the identity that will help us? It's the very first one we learned. Starts with a P. Pythagoras, that crazy Pythagoras, yeah. We know, if I scooch you over a little bit, that sine squared plus cos squared is equal to 1. And I'm going to subtract cos squared from both sides, which will leave me with sine squared equals 1 minus cos squared. I see this in my equation. And I know that thing that I just underlined in blue is equal to sine squared. So I can replace it with sine squared. What is the square root of sine squared? Louder, Valeria. Sine theta. Very good. The square and the square root undo each other. And we get sine theta. Happy, happy, happy. Couldn't have done that while I was standing at the computer, guys. Come on. Okay, so we know what the half-angle formulas are. We know kind of where they came from. Let's use them in 2 examples to see what they look like in practice. Yeah. It's gonna be okay. I promise. It gets better. It will get better. First example. We're going to find the exact value of sine of 15 degrees. And we're going to do that using the tools that we just learned. So our half-angle formula. Why do I need a half-angle formula to help me find an exact value? Yeah. 15's not on here. 15 degrees is not on here. I can't find it on the unit circle. I need to rewrite it in terms of something that is on the unit circle. So my suggestion would be, let's tackle this as sine of 30 over 2. Half of 30 is 15. That's mathematically correct, yeah? And that's a half angle, which means I can use a half angle formula to help me solve. Yeah. The other piece, I know when I use this formula, it's going to give me some other trig function, like a cosine or a sine. So I need a unit circle to help me. You guys have them at your table. I'm going to pull one up on the board for us. Not there, you stupid computer. Okay. So let's write our half angle formula out and then plug some numbers in and simplify. Yeah? So I have a half angle of a sine, my sine half angle formula. Sine is plus or minus the square root of 1 minus cos over 2. And I left parentheses there without writing anything in them because I want you to help me fill them in. So remember that if I have sine of theta over 2, I get cosine theta. This is my theta over 2. What is my theta? What's in the numerator of that fraction? 30. Which means here should be 30, not 15. That was the whole point of doing this. I need a trig function of an angle on my unit circle. Once you've got this in terms of trig functions that are on the unit circle, you grab the related fraction, you substitute it in for the trig function. So our next question is, what is cosine of 30 degrees? So let's go to our unit circle. 30 degrees is right here. Here is the ordered pair that goes with it. Is cosine the x or the y? It is the x. Very good. So I want square root of 3 over 2. I am replacing cosine of theta with the fraction. I am not substituting the fraction inside the cosine. Cosine of 30 is equal to the fraction. So this whole expression disappears, and it's replaced with the fraction that it's equal to. So this is going to become plus or minus big square root 1 minus square root of 3 over 2 all over 2. No more cosine, right? We evaluated the cosine. Cosine is gone. Which means the trig portion of this problem is done. Now it's algebra. I need to make that answer pretty, because it is not pretty right now. So let me scooch you up a little bit. As a mathematician, there are two things that make me unhappy in this problem. One is I have fractions inside of fractions. Frowny face. Two, I have a square root and on the denominator, right? Square root of 2 is in the bottom. Makes me unhappy. I don't want square roots in bottoms. So we need to get rid of the fraction inside of a fraction and then fix the denominator. So question is, what can I do to fix the fraction inside of a fraction problem? And Daniel's doing this, and I agree. We should multiply the top by 2, because that'll get rid of the fraction in the top. But if I do it to the top, I also have to do it to the bottom. Yeah? I can't introduce a number other than 1 to this problem. Otherwise, it changes the whole thing. It's no longer equal to sine of 15. Yeah. Equals plus or minus big square root fraction. And we write the simplified fraction. In the numerator, we have to distribute the 2. 1 times 2 is 2 minus square root of 3 over 2 times 2. What happens to those 2's? They cancel. That's why we did it. So it's just square root of 3. Happy face. In the bottom, what do we get? 4. Perfect. I have a question for you. What is the square root of 4? 2. Meaning this is this. Is that pretty? No. Did it fix the two problems that I have mathematically? Yes. I no longer have nested fractions. I no longer have square roots in the denominator. meaning this is as pretty as it's going to get. Yeah, I can't really do anything about the nested square roots. That's just, it is what it is. Sometimes trig is ugly. Yeah. We're going to do one more together. Yeah. And then I will set you loose on our hunt. Excuse me. Excuse me. Excuse me. So this example, they gave us the thing we were looking for, find sine of 15. Sometimes they give us sine of theta equals 1/2, find cosine of theta over 2. Meaning they give us a related trig function, but not the trig function we're interested in. How do we find it? And the answer is right triangles. So we're going to do one of those problems so you know how to tackle those. Yeah? All right, so example 2. We know that sine of our angle is equal to -4/5. And we know theta is in quadrant 3. And we want to find tan of theta over 2. So first problem is I have sine of theta. I want tan of theta over 2. That's no go. I have to fix this guy so he's in terms of theta. Yeah? So let's use one of our half angle formulas. Does anybody have a suggestion for which half angle formula I could use here? I can see. Sine theta over 1 plus cos theta. I like that because there's no square root. I also like that because I have the numerator already. I know the numerator is -4/5. I just got to figure out cos theta. Yeah, perfect. So to figure out cos theta, we're going to draw our right triangle. Yeah. So off to the side, quick and dirty. Here's the quadrant coordinate plane. I know I'm in quadrant 3, so I'm over here somewhere. Right? Oh, no, that's 4. I saw that confusing face. Yes, no, thank you. Thank you for catching that. Quadrant 3, I'm over here. 1, 2, 3. When we draw our right triangles, we drop our line down to the x-axis. So x-axis is up here. This line goes like this. My right angle, this is the angle of interest. Yay, happy face. We're given sine. Sine is what over what? SOHCAHTOA. Jennifer, what is sine? Opposite over hypotenuse. Very good. So the opposite side is 4. The hypotenuse is 5. I'm not going to worry about sines for the moment. We'll deal with those in a second. And we can use the Pythagorean theorem. I have the hypotenuse. I'm missing a leg. So when we go to write our sine and cosine, negative, negative, because we went back and down. But when I'm doing the Pythagorean theorem, it doesn't matter because we're going to square them anyway. So right now I'm just worried about sine lengths. That was a good question. Question is, what is that missing leg? So I know it's 3 because I recognize 3, 4, 5 triangles. I know that that's 3. If you didn't, when you're missing a leg instead of the hypotenuse, square, square, subtract. So 5 squared is 25. 4 squared is 16. What's 25 minus 16? I'm pretty sure that's 9. 25 minus 16 is 9. Yeah, square root of 9 is 3. Yeah. Very good. So we want to build cosine. I already know this is true. Sine of theta is negative 4 over 5. Cos of theta is adjacent over hypotenuse, 3 over 5. And in quadrant 3 is cosine positive or negative. You've got your unit circle in front of you. In quadrant 3, yeah, negative. X is negative. On all the practice problems you're going to be doing today and Friday, that is the first step. Write out the formula you want to use. Use a right triangle to find the pieces in the formula that you're missing. Yeah? Then we just substitute in what we found and simplify. So sine theta is minus 4 over 5. In the denominator, I have 1, and then plus negative is going to become minus 3 over 5. I see something I don't like as a mathematician. What do I see that makes me unhappy? Fractions inside of fractions. I'm going to use Daniel's suggestion and multiply top and bottom by the denominator. Top by 5, bottom by 5. That's going to get rid of those fractions inside of fractions. In the numerator, 5 and 5 cancel. I get negative 4. In the bottom, 5 times 1 is 5. Minus, and then 3/5 times 5. 5's cancel. I get 3. Five minus 3 is 2. Negative 4 divided by 2 is negative 2. Tan of theta over 2 is negative 2. Yay! The process for all of our practice problems today and Friday, same exact process. Do not vary from this formula. Write out the formula for the thing you're asked to find. Use a right triangle to find the missing pieces. Substitute and simplify. Yeah? Nod your head yes. You all heard me. I have it on recording. I know you all heard me. I said it out loud.